Thank you, Professor Pai, for the invitation. Thank you, everybody, especially Dr. Shetye for suggesting my name. Thank you very much, sir. I have purposely chosen, am I audible to everybody? And my screen can be seen? Is it okay?
You are audible.
Yeah, thank you. So I have purposely chosen a topic which is different from my research interests because I was given to understand that, that the larger audience would be teachers teaching at various levels in the academic setup. So I thought I would talk about the experiments that we developed as a part of an activity which was funded by the Indian Academy of Sciences, rather the joint science education panel of the 3 science academies in India. So what I would do is I would just tell you all why this was necessary, why the academy felt that this activity was a necessary activity, and what we did. And then later on describe to you one such experiment that we developed during this course of last about 20 years. So let me just begin with my presentation. All of you all know physics is basically an experimental science. Historically, physics has developed from observations, experiments, observations from nature as well as laboratory, experiments with nature as well as laboratory. So basically it is an experimental science. But what has happened over the years is that the theory has progressed at a much faster pace, leaving the experimental physics far behind. Because experimental physics is not an easy task. The instrumentation improves daily. The complexities of experiments increase day by day. So it's like setting up a factory, and that cannot happen over a period of time that and the experimentalists have really lagged behind the theoreticians. So, but unfortunately, this is what I'm talking about is at the cutting edge research. But unfortunately, this has also come into our teaching curriculum. We as teachers have found teaching physics through theory classes is much more easier than through experiments. And over the years, the experiments have been neglected. There are many reasons. It is just not just teachers themselves. There are many reasons. Primarily, there are funding issues. There are the infrastructure issues and things like that. But whatever the reasons may be, we as teachers have found it much easier to teach the subject through a class than in a laboratory. And laboratory has been a secondary activity as such, which thing like that. So am I still audible, right? Because the power has gone here, so I'm not really sure whether I'm connected.
You are audible.
Okay, fine.
You're audible.
Yeah, thank you. Science Education Panel of Indian Academy of Sciences actually thinks over or strategizes or actually takes a stock of all the science education in the country. And in 90s, when Professor Mukunda, another very celebrated theoretical physicist, was the chairman of this science education panel, the panel came out with a suggestion, and they decided to conduct refresher courses for teachers to improve the quality of science education throughout the country. And one of the things that the panel realized that if the quality of science education has to be improved, then the quality of laboratory experiments or laboratory courses also has to be improved. And as I said, the laboratory infrastructure, especially in the subject like physics, is very demanding in terms of finances, and therefore it was always set at the background in our colleges and universities. So Professor R. Srinivasan, who was a professor of physics at IIT Madras for more than 2 decades, was entrusted this responsibility of designing and conducting refresher courses in experimental physics. And he has several achievements to his credit. I just want to talk about a few of them because it will just, for those who don't know Professor Srinivasan, would get an idea of his. Today he is about 89 years old and he's still very active. So that apart, he after his retired superannuation from IIT Madras, he was the director of what was then called as Inter-University Consortium for Department of Atomic Energy Facilities. Today it is known as UGC-DAE Consortium of Scientific Research. He was the one who built that institute because he was the second director of that institute. Professor Viji Bide was the first director. Srinivasan was the second. They actually built this institute by under their leadership. And then later, after as director, he came to Raman Research Institute. This was in the early 2000, 2001 or so. And he, along with Professor Hema Ramchandran, he built the cold atom lab. That was at the age of 65 or 70. So it is at that time, the Professor Mukunda asked him to lead this exercise of conducting refresher courses in experimental physics. So Professor Srinivasan had very fixed ideas, very well thought ideas. He wanted to revamp the experimental education in physics in the country, especially at the undergraduate and the postgraduate level. He wanted to introduce better instruments for measurements. For example, thermocouples instead of thermometers, digital meters instead of analog, and he advocated very strongly. But all this requires a lot of money, and therefore, in order to make this equipment cheaper or available, to make them available at a much cheaper rate, he decided that we should develop our own experimental setups and circuits. We should build our own circuits. So initially about 6 or 7 refresher courses we conducted wherein the participants would actually build the experimental kits, and then they would be gifted to the institution of the participants, to whichever they belong to, so that they could go back and teach their colleagues and things like that. But on the suggestion of IAPT, Indian Association of Physics Teachers, Academy decided to license the building of this, manufacturing of these experimental kits to a company called Messrs. Ajay Sensors, which is in Bangalore. And they would then make them available at a much cheaper rate because the prices were controlled by the Academy. And that's how this course progressed. This was about from 2007, 2008 till about 2020. Professor Srinivasan and all of us have conducted more than 100 refresher courses all over the country, from Srinagar to Kanyakumari, and from Aizawl and Tripura in the east to Bhavnagar in the west. So we have actually traveled the entire length and breadth of the country, and rather than saying that we traveled, Professor Srinivasan at his age of 80s, in his 80s, also traveled along with us and stayed there and conducted these experimental refresher courses. So what we developed, the plan was very clear. We wanted to provide physics laboratories the necessary infrastructure that is required to conduct a teaching experiment. So we built constant current source, we built laboratory power supply, furnace, temperature controller. We also built experiments that would allow the students to verify some fundamental laws like Stefan's measurement of Stefan's constant. Stefan's constant is related to h by e. So you could measure Planck's constant, for example, if you knew the charge, or you could estimate Planck's constant if you knew the charge. Thermal and electrical conductivity of a metal, you could estimate Boltzmann constant if you again knew the charge of an electron. Dielectric constant of polar molecule, you could estimate the size of the molecule by measuring its polarizability. Or you could, if it was a non-polar molecule with a permanent dipole moment, you could measure the dipole moment, or what is the displacement of atoms when the dipole moment is created, or displacement of charges when the dipole moment is created in such molecules. So this was the these were the goals, like thermal diffusivity, another very, very important experiment. Because we see diffusion in the phenomena of diffusion in everyday life. Diffusion is very common in every sphere of our life. Solids can diffuse into each other, liquids can diffuse into each other, gases can diffuse. Not only that, liquids can diffuse into solids. So it's like any medium can diffuse into another medium. But the beauty of physics is there is only one equation that governs this entire phenomenon. And so if the students can appreciate this underlying beauty of the subject, or you can take example of relaxation, another very important phenomena in physics. So we developed some novel experiments also, which were hitherto not available in the market, or they are still not available in the market except for Ajay sensors. So we started thinking of how we can improve the laboratory infrastructure, and all this at a price which would be 1/10. So for example, we also built lock-in amplifier. If you go and buy a lock-in amplifier in the world is manufactured by only 2 companies. That is, one is Princeton Applied Research, which is an offshoot of Princeton University in the US, and the other one is from Stanford Research System, which is an offshoot of Stanford University. These equipments are very good equipments. They use digital signal processing technology, and they cost a lot. The minimum cost of this is about 3 to 4 lakhs, and they run into tens of lakhs as you demand for more and more better specifications. But what we thought is, if we could provide a lock-in amplifier to the students, postgraduate and undergraduate students, costing about 10,000 rupees, then probably majority of colleges and majority of universities would be able to purchase this and show their students, or their students would be able to perform experiments with this lock-in amplifier. So it won't be just a black box to them. If they happen to go for research, then they won't just see a lock-in amplifier and say, oh, what is this? I have never heard of this before. So lock-in amplifier becomes a very important tool in our physics measurement or experimental physics. Because whenever you want to measure a small signal in presence of noise, you go for a lock-in amplifier. So what I will do today is I will essentially describe to you what is a lock-in amplifier and how you yourself, if some of those who are interested, who are listening in and are interested in that, some of those can actually build it. So since now it has been licensed to Messrs. Ajay, I won't be able to give you the entire circuit diagram of the thing, but I would be definitely able to tell you what is the crux. And those of you all who have some interest in electronics should be able to build this very easily. It's not a very big circuitry, or it is not a very complicated circuit at all. Okay, so over the years, this activity started, as I told you, in 2001, and over the years we developed more than 30 experiments, and now Indian Academy of Sciences has published this lab manual, which is available along with these experiments. So which is authored by 3 of us, Professor Srinivasan, Dr. T.G. Ramesh, who was at the National Aeronautical Laboratories earlier, and myself. And although this book is not available in market because Academy academy does not believe in selling the book, but if the institution that purchases the experimental experiments from Ajay sensors, this book comes along with those experiments. So I'll begin with my description of lock-in amplifier. And if you have any questions, you can just unmute and stop me whenever you want to. So all of us know what is an amplifier, right? And so whenever we go and buy an amplifier, we buy an amplifier of a large bandwidth, several kilohertz. The reason is that any signal that comes, we would like that thing to be amplified, right? So, and we would like, so we don't want a particular frequency amplifier or a narrow range frequency amplifier. We want a wide range frequency amplifier. So its bandwidth has to be large. But whenever a weak signal is amplified, the noise is also amplified. And let us consider an example here. Suppose there is a 10 microvolt sine wave that has to be measured, and its frequency, let us say, is 10 kilohertz. Okay, so if you want to measure this, you need to amplify it. So you go up to the market and you buy a good low noise amplifier, which has a noise of about 0.5 microvolt per root of hertz, and its bandwidth is about 100 kilohertz and a gain of 1000. So this 10 microvolt signal would be 10 millivolt. And if you take this noise into account, then you can just look at this expression, the input noise of the amplifier multiplied by the root of its bandwidth and the amplifying factor, the noise itself will be 160 millivolts. So what essentially you will end up measuring would be just the noise, and your signal will be lost in that noise. So the trick is that you provide a band pass filter and you try and cut down the bandwidth, but that again doesn't solve the problem much. So what you need is a technique called as phase sensitive detection. But before that, let us understand from where does this noise come and why can't we eliminate this noise? Right. So in a laboratory, typical physics laboratory, there will be a few sources of noise. I'm just listing typical sources. These are not all the sources. There are many others. So there is something called as a flicker noise. That is because we have things that are flickering in laboratories, maybe tube lights or something like that. So they will cause a noise in the measurement, but their power spectrum is inversely proportional to frequency. So if you shift your measurement frequencies to higher frequencies, then you will be able to get rid of this noise, or you will be able to take care of this kind of noise. You would also have some motors, AC sources like motor, and like for example, you could have an air conditioner, or you could have fans or whatever, something that are running in the lab. And they would also contribute to the noise, but their power spectrum is in a very narrow range of frequency, and you could easily also eliminate them, or you could also put what is known as the electromagnetic shielding, and then you can avoid this noise from AC sources. But what you can't really avoid, or what you have to live with, is what is known as the thermal noise. The thermal noise, the power spectrum is white. And by white, I mean it is present at all frequencies. It comes about because, whatever wires that you use for measurement, they are essentially, let us say, they are copper wires. So these copper wires, they have atoms which are vibrating, and these vibrations of atoms inside that copper wire or inside all your measurement circuitry, the atoms vibrate, and these vibrating atoms contribute to a noise. So you just can't eliminate them. You can only take your entire apparatus at a very low temperature, which is not feasible, okay? Because these atomic vibrations only cease or reduce in amplitude only when you reduce their temperatures. So this noise is omnipresent, it is present everywhere, and it cannot be eliminated. So you have to live with this noise, and you have to survive with this noise. So how do you then measure weak signals in presence of such noise? So for that, the technique is called as phase sensitive detection. So let me just explain to you what is a phase sensitive detector, and then that would also lead to how you can build a lock-in. So suppose you have, now we take the same example, but instead of that large bandwidth amplifier, we have a phase sensitive detector, and which has a bandwidth of only 1 Hertz. And this will be clear to you why I'm saying this. So then suddenly the noise in that same expression, when you put the bandwidth as root of 1 Hertz, it becomes only 0.5 millivolts. So although you have not eliminated the noise entirely, and as I told you, you cannot eliminate, but in presence of a signal which is of the order of 10 millivolts, this is much a small quantity, and you can live with it. You can still measure your signal. You make a very small error here, right? So the question is, what is this phase sensitive detector, or what is the principle of phase sensitive detection? So for any signal to be generated, there has to be a cause, there has to be a reference. Okay, so signal is the effect of this cause. You can think of mutual inductance, you can think of anything that comes to your mind. You need something that will produce that signal. So the cause, we call it as the reference frequency. And I indicate it as a sinusoidally varying voltage given by this expression, Vref is equal to V0 sine omega t. And suppose the signal, which is the effect, is a very weak component that you want to measure, then that signal, I denote it by a small V naught. So just to tell you that its amplitude is small, sine omega t plus phi, because signal need not be in phase with the reference. It can have a phase difference, and that phase difference I indicate it with this angle phi. So this is pictorially what I just said. So this is your reference here that you can see, and even though you may not be able to see the numbers very clearly, it does not matter. I'll just tell you, on my x-axis, my scale is fraction of a period. So I'm showing you the sine wave for 1 period. Okay, so this is the first half cycle and this is the second half cycle, as you can see. And this is the signal. So this is the lower sinusoidal wave is the reference, and the upper sinusoidal wave is the signal. And you can clearly see that the signal is not in phase. And just I have indicated the amplitudes, while the peak amplitude of the reference signal could be about 100 millivolts. The peak amplitude of your actual signal voltage is about 100 nanovolts. Now these numbers have no meaning, as I told. These are only to impress upon you that signal is a very small component of that you want to measure. So I have just indicated them with several orders of magnitude difference, because it is only then that you would need something like a lock-in amplifier to measure that signal. Right. So there is a chip that is available in the market, which is called as AD630. When we started purchasing this chip, it used to cost about in retail around 800 or 900 rupees. Now probably in retail it is close to 2000 rupees, but in wholesale market it is much cheaper. At that time we could get it for even up to about 500 to 600 rupees in wholesale market. So this chip is available, AD630. The chip is a 16-pin IC. It has inside that, I'm not going to describe what is all there in that, but the crux of the whole thing. There are two identical amplifiers. You can think of op-amp amplifiers. One is a direct amplifier and one is an inverse amplifier. Identical meaning they have exactly the same gains. So what it would mean is that if a signal is applied to a direct amplifier, then that signal will come out as the amplification factor alpha, or the gain alpha, times the input signal, right? Whereas in the inverse amplifier, the output would be minus alpha times the signal V over the signal voltage. So these are identical in all respect. Now, to who decides, there has to be, you realize that there has to be somebody to decide whether whatever you give the signal to this chip, whether it should go to direct amplifier or to inverse amplifier. So there is a policeman who controls this traffic, okay? And that policeman, in physics or electronics term, we call it as a comparator. So when the comparator output is along the plus side, whatever signal comes goes to direct amplifier. When the comparator output is on the negative side, whatever signal comes goes to the inverse amplifier. So it doesn't depend on the sign of the signal, it depends on the output of the comparator. And who decides the output of the comparator? The output of the comparator is decided by the reference signal, the cause that created this signal. That is responsible for this signal. Okay, so if the reference signal is positive, the comparator connects the signal voltage to direct amplifier. If the reference voltage is negative, the comparator connects the signal voltage to inverse amplifier. So that is how it looks here. So this is the policeman or the comparator, and these are the two identical amplifiers. And there's whatever signal you give here, signal voltage you give here, depending on the sign of this voltage, it goes to either the direct amplifier or to the inverse amplifier. And then there is an outage. So in order to make it more clear from the figure, so when the reference signal is positive here, this is the reference voltage which is positive here. So this is the first half period. Whatever that is indicated, that is available here, so it's some part of it is positive and negative, will go to the direct amplifier. So you should see the same type of voltage or same type of curve in my output, right? And I will show it to you in a minute. Whereas whatever is available now, the next half cycle of this reference wave is then given to the inverse amplifier. So if it is negative, it will appear as positive, and if it is positive, it will appear as negative. So that's how your output waveform will look like, okay, for that particular two cycles that I showed you, reference and the signal cycle. So you can see this is basically a something that is reminiscent of a full wave rectifier output. So it has got it is basically a DC. It has got an average DC with small AC voltages appearing at frequencies like omega, which is the signal frequency, or harmonics of that, 2 omega and 3 omega and so on and so forth. And these components can be filtered out. So what you get from a phase sensitive detector by just doing this is you get a DC output which is proportional to your signal output. So how do you then maximize this, or how do you know that this is exactly what it is? So the best thing is to knock off these negative things here, so, and to make the entire thing positive. So what do you do with that? So you see, what you do is we just write this in terms of mathematical expression. So what you did was whatever signal that came for the first half cycle from 0 to T/2, you integrated it by giving it to direct amplifier. And whatever came in the next half cycle from T/2 to T, you fed it to the inverse amplifier, so that for that negative sign comes. And if you solve this integral, then the DC voltage that will be available to you will be given by 4 alpha V0 by 2 pi into cos phi. Now, those of us who are physics teachers would immediately realize that if I remove this cos phi, then it is nothing but the output of a full wave rectifier. So you can see, how do I take care of this cos phi? There is a trick, right? Cos phi, when the phase angle is 0, or the phase difference between the reference and the signal is 0, cos phi will be 1. So what I have to do is I have to shift the phase of my reference wave to match with the signal wave. And since cos phi cannot take any value greater than 1, the DC voltage that will appear when the phase matches will be maximum. So I don't touch the signal because that is what I need to measure, and we don't never touch the signal, but we can play with the reference cos, okay, and we can shift its phase to match with the signal phase, okay, such that the DC voltage that is produced is maximum. It's a pure DC, and that is what is available. So what do I need to do? I need, in addition to whatever circuitry I showed you, before the reference voltage is fed to the chip, I need it to pass through a phase shifter or phase shift oscillator, or a phase shifter basically, that will allow me to play with the phase or to match the phase of that reference signal with that of the one that I have to measure. Okay. So if I am able to do that, then the output of the AD630 will look something like this, and then you will have a maximum DC voltage. Now this, whatever I have described to you, is called as phase sensitive detection, because it is sensitive to the phase of the signal voltage. So whenever the phase is matched, I have maximum DC voltage available to me. So that's how I can measure. Okay. Now the question is, how does it take care of the noise? That's how we started. Our initial problem was with the noise, right? So suppose the noise is appearing at any other frequency other than the frequency that you want to measure, your signal frequency. So let me call that as an F prime here. Whatever voltages that come at other frequencies other than the frequency of measurement, okay, we call it as noise. That's what we don't want, right? If the integration time is large, let us say of the order of 1 second here, okay, then the contribution of the noise to the VDC will decrease rapidly as F prime differs from F, because F prime minus F, you can call it as a delta F. So VDC noise will be essentially V noise, the amplitude of noise, into cos of delta omega t. That's exactly coming from the previous expression that I had written. So what will be the average value of this noise over 1 second, which is roughly the integration time of your amplifier, will be alpha times this expectation value of this quantity here, which you can see that it will be 0. So even if the frequency differs by an order of 1 hertz, your noise will go down to 0, right? So you will be measuring essentially only that value of voltage which is coming at the frequency plus or minus, let us say 1 hertz, that is coming. So this is true for our lock-in amplifier. The ones that I told you, which are available commercially in the market from SRS or Princeton, their bandwidth is very large, integration time is very large, 1,000 to 10,000, and that's what demands the price. Okay, so you actually can measure nanovolt signals in using those, whereas the one that we have built, you can measure about a microvolt signal. 1 microvolt you can easily measure. So which is good enough for a teaching laboratory. You would still be able to explain to your students the principle of lock-in. You would still be able to explain to them what is phase sensitive detection, and you will be able to do very good experiments along with that. So the name lock-in amplifier comes because it locks to a very narrow range of frequencies around the frequency of your signal voltage. So that is why the name comes as lock-in amplifier. So what I have told you is now that the output of a lock-in is a DC voltage, and you are giving an input signal and sinusoidally varying signal. So there has to be a connection, or you should know the connection between the output and the input that you feed, because your aim essentially is to measure the input signal. So you need to calibrate that instrument. So we need to provide you a calibration circuitry. Now in the commercial, again, this is all done. So this is all done automatically. So you never really do it, but that is the black box part. So we thought we should include a calibration circuitry that allows you to calibrate your lock-in, and that's how you can learn how the lock-in works, right? So for calibration, inside the lock-in box, what we have provided is a series of 3 resistances, 220 kilo ohms, 10 ohms, and 5 kilo ohms. They are connected in series. So this is like that. The circuitry is like this. And this is the lock-in amplifier now that is available from Ajay Sensors. So I will spend some time in explaining to you how it works and what you can do, and then come to calibration part of this. So, okay, so first let us think of this pin. So your signal, whenever you are calibrating, your signal generator is connected to this pin marked as SIGGEN. Okay, and the output of the lock-in is available at this pin called as output, where you need to probably connect a DC multimeter or a DC voltmeter here that will measure the DC voltage. Okay, now these 2 pins, which are called as reference pins, this is where you supply your, this is where the reference and phase shifted reference output is available. At these 2. So one of them is the reference output and one of them is the phase shifted output. You should connect these to a CRO, a dual channel CRO, and then you will be able to see the 2 sinusoidal waves. Okay, and if you put that CRO in external mode, then you will see a Lissajous figure, right? And that Lissajous figure will tell you what is the phase difference that you have to give in order to make your DC output maximum. So when the DC output is maximum, it means that the phase of the signal and the reference have matched. So that's how you can check that here. Okay, and what decides whether you are calibrating or not are these 2 switches here, which are on the top, on the left corner of your figure here on the top. These 2 switches, when they are put in on the internal side, the circuit, the lock-in amplifier goes in calibration mode. That means when you connect the signal generator here, it is fed to this resistive network, which is inside this box. Okay, and this knob here is the phase shift adjustment knob. So you can continuously adjust the phase angle between the reference of the reference wave. Okay, and when you want to measure an external signal, you just put these 2 switches on the outside. So it goes as external. It is marked also here, EXT on both the sides. So both the switches you put on the outside, and you connect your external signal that you want to measure to these 2 pins here, which are below that. There is a marking called as external signal, and the reference voltage that you want to give from outside, you give it to this pin. Rest everything remains the same. These top 2 pins are for testing. This pin is the actual signal voltage. Say for example, you are doing calibration, then the signal voltage that is available across this 10 ohm resistor will come here, or whatever you give at this external signal, that can be measured from here if you would like to see it. And this pin 13 is the output. I showed you the full wave rectified output of the lock-in. That rectified output can be displayed on the CRO from here. So this is only to help your students to understand how the lock-in works. Okay, so when you give a signal, when you want to calibrate the lock-in, you give a signal to these 3 resistances, or this ladder network of these 3 resistances, you realize that the voltage that is developed across this 10 ohm resistor, which is what we call as our signal voltage, would be given by this formula here. The RMS voltage that you supply divided by the total resistance of the network, which is here, multiplied by the value of that resistance. So I know exactly if I give 1 volt AC RMS voltage, my signal voltage would be 44.4 microvolts. So I exactly know what is the relation between my input and the signal. So I can measure my DC and establish a relation between the DC output of my lock-in amplifier versus what is the signal voltage. Okay, so that's what you do as a calibration experiment. At different frequencies, you supply some VAC. I have indicated here peak to peak because commercially, if you use the signal generators that are available commercially, they don't give you RMS values, they give you peak to peak values, but it is okay, you can always recalculate that. So you can get the signal voltage here, okay, from that formula, and you measure this DC, right? And you can plot a graph of the DC output of your lock-in versus the signal voltage that is available here, and you will see that it is very linear, perfectly straight line, everything. And you can actually look at the readings, they are almost the same irrespective of frequency. And that means the slope of this line is almost the same. So if you do it at several frequencies, the lines will almost interpose on one another. And you can see that the frequency is the slope is almost constant, almost the same. There is about 3% error between the mean and the largest deviation is about 3% from the mean. So that is roughly the error bar that you have in measuring, about 3%. So you can actually see how good the fits are, and you can do it over a wide range of frequencies, few hundred hertz to about 10 kilohertz. So it is very good for any laboratory experiment that you want to measure. And roughly it is about 5,000 something. So it is for this example what I have taken, it turns out to be it is 5,320 is the amplification factor. So whatever voltage you give, it is amplified 5,320 times, something like that. Yeah, so you can do some experiments with that. One of the experiment that as a physics student we all dread to measure, or the one that is ridden with a lot of errors, is the mutual inductance experiment, because the induced voltage in the secondary, because of some current flowing through the primary, is always small, and especially if there is no coupling between them, and air is the coupling or air is the medium. So, and then we as students we always dreaded this experiment. So I would show you how easy it is to do it using a lock-in, and you could verify all the three Faraday's laws that we know of, that the induced voltage in the secondary is 90 degrees out of phase with respect to primary current. It is proportional to the magnitude of primary current, and it is also proportional to the magnitude of frequency. All these three laws can be verified straight away. So what we have for our mutual inductance, we have built our own setup for mutual inductance, and it's very easy. So it's just take a former, a plumbing pipe of 2-inch or 4-inch, 2-inch diameter, 2 or 2.5 inch diameter, and you just wind two coils. One you call it as primary, one you call it as secondary. The secondary coil, you wind several times more turns than the primary. That's all. And you physically separate them by a certain distance. You can decide this distance, whatever, 1 inch, 2 centimeters, whatever that you want. Along the primary side, you just connect, again to make that same kind of ladder network, you connect a 4.7K and 100 ohm as shown here. Okay, and you can connect the signal generator to the whole thing. And then across 100 ohm, the voltage that is developed can be taken as the reference voltage and give it to the pin called external reference, and the secondary voltage that is developed can be given to the pins called as external signal to the lock-in amplifier. So that's it. This is our the mutual inductance coil. So you can see the primary and the secondary, and then you make the connections with the lock-in amplifier here. And just to show you what you are going to do, you know that this is the expression, the induced voltage is equal to minus m times omega I naught e to the power I omega 2. So I naught e to the power omega, this part I write it as I, and therefore the mutual inductance M would be given as V over 2 pi Fi, right? And what is this V? This is the signal voltage or the voltage that is induced in the secondary. You feed it to the lock-in, you get output as DC voltage. How is this DC voltage connected to the secondary voltage? It is connected by this expression here. VDC by mu is the signal voltage. Mu is your a calibration factor of the lock-in. And this current you can estimate from this ladder network because the total resistance of the ladder network will be 4.7K plus 100 ohms. The resistance of the primary coil will be negligible, okay, few ohms. So it will be around 4,800. So this R I know it is 4,800. If whatever RMS voltage I pass through that ladder network of primary coil, I will be able to calculate the current from there. So I substitute for current VAC by R and then I get this. So if I plot a graph of VDC versus VAC, I will get a slope alpha. Okay, and if VDC is proportional to VAC, it tells you that the induced voltage is proportional to the current, right? And then this alpha, if I plot it along as a function of the frequency f, then I will get a slope beta. And if this is a straight line, that means my VDC or the induced voltage is proportional to the frequency. So thereby I have verified two laws of Faraday. How do I verify the third law? Well, when you connect this thing, you will have to shift the phase to make the output voltage maximum. Okay, and you will realize that the output voltage is maximum when you shift the phase of your reference by 90 degrees. So if you observe a Lissajous figure on your CRO screen, it will be a circle. When the DC voltage on your multimeter is maximum, the display pattern on your oscilloscope will be a circle. So you would know that the induced voltage is at 90 degrees out of phase with respect to primary current. So this is exactly the way you can verify all the three Faraday laws. And these are some typical readings. And these are the graphs that you can see that the proportionality with current is seen because this is the RMS AC voltage in or the current quantity that is proportional to current. And you can see the slopes are increasing with increasing frequency. So therefore, it is also proportional to frequency. And if I plot my second graph to estimate beta, then beta is here. And you can plug that in this expression here, and you know everything else in that, okay? And then you will get something like 77 microhenry. So it's easy, it's reliable, and you can verify the laws very easily, and you can convince your student that physics actually works in the laboratory. This is something that we have been lacking in convincing our students many times, because the instrumentation that is available to us, because of whatever be the factors that are responsible, lacks in accuracy. So lacks in precision. So that's where you can do these experiments very simply. The last part that I would talk about is measurement of low resistance. Why? Because resistance is one quantity that varies over several orders of magnitude. You have insulators which have giga ohms and tera ohms of resistance, whereas you have superconductors which have zero resistance. So it's several orders of magnitude, and what is stuck in our mind is whenever we want to measure a resistance, you can just pick up a multimeter, connect the two probes and measure. It's wrong. There are techniques to measure resistance depending upon its value. And we learn it as students of physics, we learn it, but somehow it does not get percolated, right? So there are constant current sources, there are constant voltage sources. You can measure very high resistances by discharging it across a capacitor and measuring the time constant. You can, when you want to measure very low resistance, you can use a lock-in. So we have also built a lock-in circuitry for measuring low resistance. It's the same thing. The low resistance is connected in series with 4.7K and 100 ohm resistor. And you can use this circuitry in the same way. The procedure and everything remains exactly the same. And you can measure the resistance. So what we are saying here is that if a current through that small low resistance changes by DIAC, then the voltage, it will produce a voltage change of DVAC, right? And this the voltage that is actually available across that low resistance will be proportional to DIAC. So that is what we do, and we we measure the DC equivalent of this. So that is, I have written here dVdC, which is nothing but mu times dVr. And so if I substitute all that, then I can get my value of low resistance, which is the small r, is equal to mu times mu upon r. And I know this slope. I just have to measure this slope. So I do the experiment. I measure the slope. Okay, you can see that as a function of frequency, again the slope remains almost same, and you can estimate a value of resistance. In our case, we have taken something around 0.1 or 0.2 ohm resistor, and this is a handmade resistor. It is very easy to make. You just take a length of copper wire, fold it into two, and you have a resistor there. So that is why I said that resistance value is around 0.1 to 0.2 ohms. You can look at the error or the precision with which you can measure that value. It works fantastically well. So I think I have come to the end of my presentation. If there are any questions, I will be happy to answer. Thank you.